We're going to look at properties of logs, and it is important to understand if I said log base b of n is e, the equivalent exponential is b to the e equals n. And we know b stood for the base, and e was the exponent, and b to the e gave us a number. That's what we called n. So it's important to realize when you see log base b of n, you're coming up with an exponent answer. When you see any logarithm, the answer is an exponent. So logs represent exponents. And it's the exponent that when you took b to that power, you got that number. But any log is an exponent. So because they're exponents, the rules that apply to exponents become properties of logarithms. So for example, suppose I told you you had a number a, and that number was b to the m. We know from our previous work that the log, if you took that base b of that number a, would be the exponent little m. But now let's look and say we had a number capital B, which was little base b to the nth power. That means that the log base b of capital B, that number, is the exponent n. We now want to investigate what happens when we multiply a times b. Well, each of a and b are actually powers of little b. So a is b to the m, capital B is b to the n, and so for our rule for exponents, when you have the base appearing twice like this, when you're multiplying two exponentials, you add the exponents. So we will add those exponents, and this will be b to the m plus n. Now when I ask about the log of a times b, base b, I'm really asking about the exponent of ab when b is the base. And we see that the exponent is m plus n. But I know that m is log a base b. So I can replace m with this log. I can write log base b of a. And now I see that n is the exponent of b. So it's log base b capital B. So what I have is the first property of logs. It tells me that when I multiply two numbers, the exponent from that multiplication is the sum of the exponents of the others, because I added exponents originally. This rule and property is very important, so we summarize it like this. The exponent or log of a product is the sum of the exponents. So the exponent of a product is you add the exponents, so the log of the product is log of 1, the exponent of 1, plus log of b, the exponent of the other. And this is one of the first properties of logarithms. As an example, so it becomes a little more concrete, for example, if I said log of 8 times 11, and because I'm saying log without a base, it's understood the base is 10. According to this, it would be the log of 8 plus the log of 11. We can do this because we have our calculator. This is a log, which is known, base 10 is a common log. So the log of 88, I can work this through with my calculator, and I see that number is 1.944482. Now all I have to do is look at and that's the big question, look at the calculator value for log of 8. And I get that that value is 0.9030899. And then I get the log of 11, which is 1.041392. And if we proceed to add these two, we'll see that aside, I had some round off problem here, but if we add these two, they will add up. So this is demonstrating just by calculator values that when you multiply two numbers, their exponent, log, is the sum of the exponents of each of the pieces. So that's one way that we can see this. Now that we understand that logarithm is an exponent, we're going to look at another situation. What if I wanted the log base b of a divided by b? I want the quotient of two numbers. Well, we look back again and we found that a was b to the m. Capital B, that number, was b to the n. If I do a over b, I'm doing b to the m divided by b to the n. And from our rules of exponents, we know that we can subtract those exponents. So a over b becomes b to the upper m minus lower exponent, m minus n. Putting this here, I see that this is just m minus n. But I know that m is the exponent for a, so this becomes log base b of a minus n is the exponent of capital B, log base b of b. I now have a second property of logarithms. That second property is log base b of, when you divide, the exponent of the quotient is you subtract their exponents. We'll go on to the next page and we can try this with a common logarithm. So for example, if I said log, the common log, we're going to do base 10 of 10 divided by 5. According to this, that is log of 10, the upper, minus log of 5. But 10 over 5 is 2, so we're really looking at the log of 2. And you will see, is that log of 10 minus log of 5? Well, log of 10, 10 to the 1, this is going to be a 1 minus log of 5. Log of 5 is 0.69897. It goes on and on. And it turns out when I do 1 minus that, I get 0.301029997. When you put 2 into the log on the calculator, you get the same exact answer. So it corroborates this second property of logs. Now we'll get the third property of logarithms. And in this property, I am looking at, suppose I said log base b of a to the p power. Looking at what we just did, we said a is b to the m, but now we're doing a to the p power, which is b to the m raised to the p. But we're just going to be multiplying this exponent, and this is b to the p times m. So we are asking, what's the exponent of a to the p? And that exponent is p times m. But that is p, and we know that m is the exponent of a, so it's log base b of a. So that gives us our last property of logarithm. And that property tells us that when you want the logarithm of a number raised to a power, you just take that power in front times the exponent of the number. So there's your p times m. And that's our third property of logarithms. To try an example, I might say, what is the log? Again, it's a common log, base 10, of 2 cubed. According to this property, the 3 will go in front. So I'm going to move this 3 in front. And this becomes 3 times the common log of 2. And it's 3 times 0.3010. I'm just going to do 4 places. So it looks like it's 0.9030. But 2 cubed is 8, so I'm looking at log of 8. And when I put log of 8 in the calculator, I get, just to 4 places, 0.9030. So it shows this property works very nicely.